Back. This is question number 3 from May-June 2017, paper 4, variant 1. Another question on transformations. There's a few parts, especially at the end of this question, which are quite important. I will go through the whole question, however. Let's start with the beginning. It says, draw the image of triangle A after reflection in the line x equals 4. So triangle A is a shaded triangle here, and we have to reflect it in the line x equals 4. Now, as we mentioned before, the line x equals 4, okay, is a line, okay, where x is always 4. Okay, so the line where x is always 4 is a vertical line that goes through 4 on the x-axis. So this is the line x equals 4. Okay, that's the line x equals 4. Okay, that's the line x equals, x equals 4. Now, if we want to reflect something in the line x equals 4, basically, what we have to do is we have to count the squares, okay, that the distance away a point is from the mirror line, which is x equals 4. So, for example, this point here, see how far away is it from the mirror line? 1, 2, 3. It's perpendicular distance from the mirror line, okay? The distance at right angles to the mirror line, which the mirror line is vertical, so that distance is going to be horizontal. So it's 3 squares away from it to its left. So its image is going to be 3 squares away from its on its right. Okay, so the distance of the object, okay, of the image from the mirror line is the same distance as the object from the mirror line, but just on the other side of the mirror line, along a line which is perpendicular to the mirror line. Okay. So, for example, this point as well is going to be over there, and this point is going to be over here. So we have the 3 points that we need. We can just join them together with a straight line. Okay, the straight line. Yeah, there's a line. Okay. So I join that to that, and I join that to that, and that to that. Okay, that's my reflection in the line x equals 4. Okay, so draw the image of triangle A after reflection in the line x equals 4. Okay, so that's that. Now I'm going to label that as A part 1, just to make it clear. It's A part 1. Let me just straighten up this line. It's gone wonky there. Okay, now then second part of the question. Draw the image of triangle A after a rotation of 90 degrees anticlockwise about 0, 0. Now, the easiest way to do this is to use tracing paper, okay? After a little while, you probably not need to use it, okay? But I'll just show you how to use tracing paper. And something in an exam you can do. Your examiner, your invigilators are supposed to provide tracing paper if you ask for them. Now, if in case they don't, you could ask your maths teacher to ask the examiners or to give some to the examiners before the exam. You could take some yourself and give it to the examiners before the exam. Don't take it in with you. Just say, look, here's some tracing paper in case you don't have any. That's one of the materials we're allowed to take, as it mentions on the front of the paper. So if you want to do that before the exam, that would be a good idea. So I'm just going to get the tracing paper ready. Okay, so here's some tracing paper which you place over the shape and you trace it in. That's already traced it over. Okay, so you place the tracing paper over your shape, you trace over, okay, the triangle here, and then it says, what does it say? Rotation of 90 degrees anti-clockwise about 0, 0. So you would take your pencil and place it over 0, 0. So you take the pencil, okay, and you place it over the origin, okay, which is over here. Okay. Just get that right. Okay, so you'd place the pencil right there and keep the pencil there, and then what you would do is you would basically just turn the tracing paper anti-clockwise, the opposite direction from the clock, until you've gone through 90 degrees. See this red dot that I'm pulling at the top here? When this is facing horizontal, then you know you've gone through 90 degrees. Boom. Okay? So this is now the position after it's been rotated 90 degrees anti-clockwise about the origin. Okay? So that's now, I'll just mark those points so that we can see where we are. So you mark the point here, and there, and there. Okay? And you take the tracing paper away. Oops. When you do this, of course, you have to kind of lift the tracing paper up and then put the dots down, or just remember in your mind where it was. It's not too difficult. And there we have the the rotated shape. Okay? So that's now the answer for part 2. So that's A part 2. So I'll write here, I'll write in the shape A part 2. A part 2. Okay. Now, the next part says, draw the image of triangle A after a translation by vector 1, 5. 1, negative 5. 1, negative 5. Okay? Sorry, pen. Okay. Now, 1, negative 5. So, translation, 1, negative 5. So let's choose one point. For example, let's choose the right angle again. We're going to go 1 to the right. See, the number of units is the same as the number of squares, so no problem. 1 to the right and 5 down. So you're going to go from 1 to 2, and then 5 down, you'll end up at negative 4. Okay, so that right angle is going to go from, it's going to go 1 to the right, and 1, 2, 3, 4, 5 down. And then from there, we can pinpoint everything. This line has to be 3 squares up. This line has to be 2 squares across. With the translation, everything stays in the same relative position. You don't have to worry about anything else. Just draw it, and there it is. There's A part 3. Okay, that's A part 3 done. All right, so there, so far, that's A. Now, then it says, describe fully the single transformation that maps triangle A onto triangle B. Now, triangle B is over here. Okay, the single transformation that maps A onto B. Now, you can see A and B are different sizes. All the transformations that we're doing, translations, rotations, reflections, okay, those 3 of them will, the object in the image will always be the same, like, shape and the same size, just rotated or reflected, just moved around or reflected or rotated, but they're the same shape, the same size, okay? The only transformation that you have to deal with in your syllabus is that in which the shape, the size of the object and the image are different, is enlargement. Okay, their shape is the same, they're similar, but their size is different. So you know for sure, if you see something that's smaller or bigger than your original, you know it's got something to do with enlargement. There's nothing else that you have to deal with in your syllabus. Okay, so for enlargements, the way to find, the enlargement is defined by saying it's an enlargement, giving the center of enlargement and writing down the scale factor of enlargement. Okay, so now, here in this case, in any case, to find the center of enlargement, you join an object to its image. So I'm joining a point, okay, like this pointed angle at the top, the smallest angle to the smallest angle. I can join the right angle to the right angle. They have to be corresponding points. Where they meet is the center of enlargement. If I did the same for the third point, they would also meet that point. You just need 2 of them to pinpoint the center of enlargement. So here is the center of enlargement. Okay? I'll just call that E. Okay? And the coordinates of that point are 5 and 5. That's the center of enlargement. Okay, so when we describe this, we can say it's an enlargement. Even though it's got smaller, you still call it enlargement. The scale factor, sorry, let me write the center first, and then we'll deal with the scale factor. The center of enlargement is 5, 5. So the center is 5, 5. You give the coordinates of the center of enlargement. And the last thing is the scale factor. Now, how do you deal with the scale factor? Well, we always have image divided by object. Okay, this is A mapped to B. Okay, so this is the image, and this is the object. All right. So you take a length on the image. So, for example, let me take from the right angle across, from the right angle to this point. Okay, this is going in the negative direction. Okay, 1 space to the left. Let me take the right angle in the original object. This goes 2 spaces to the right, so it's positive 2. Okay, so the scale factor is negative a half. The scale factor of enlargement is equal to negative a half. Okay, so if you notice for enlargements, if the object and the image are upside down in relation to each other, then it will have a negative scale factor. Okay, and if the image is smaller than the object, okay, if the image is smaller than the object, you'll always find that the scale factor you get is its value will be less than 1. Its magnitude will be less than 1. Okay, it will be smaller than 1, its magnitude. Okay, so like if it's a half, it will be positive. Okay, and it won't be upside down. But if it's negative half, it will be upside down and smaller. Okay, so the negative tells you that it's upside down, and the actual value tells you how much each length is smaller or bigger than the original in the object and image. Okay, so that's how you work out how to describe that fully. You need 3 things for enlargement. You say it's enlargement, you give the center of enlargement, which I taught you how to find, and the scale factor of enlargement. If they're upside down in relation to each other, you'll see that the end result will be negative. Okay? Now, find the matrix that represents the transformation in part A2. A2, they described for us already as the image of the triangle A after a rotation of 90 degrees anti-clockwise about the origin. So we don't even need to look at the diagram for this. Okay, we can just come up with it ourselves. Now, some people, they always memorize all the different transformation matrices, the standard ones, and I find that to be a bit of a problem. Okay, I don't like memorizing when there's no need to memorize. Okay, sometimes there's a need to memorize, but in this case there's no need to memorize because you can do it very easily by just understanding. Okay, now the way I teach how to find the transformation matrix which represents a particular transformation is I say always start off with your base vectors they're called. So I and j. I is always at the point 1, 0, and j is always at the point 0, 1. That represents what's called the unit matrix. That's a matrix that if you multiply with anything, it doesn't change it. So that's I and that's j. You always start off in these points, these positions. Now it's saying find the matrix that represents a rotation of 90 degrees anti-clockwise about the origin. Okay, so all you need to do is you need to write down the new position of I and the new position of j after you rotate them 90 degrees anti-clockwise about the origin. So take the point I. I is always written as the first column in the transformation matrix. If you rotate it 90 degrees anti-clockwise about the origin, it's going to end up where j is. That will be I dash, which is 0, 1. And if you take j and you rotate it 90 degrees anti-clockwise about the origin, it will end up at this point here. This is called, I'm going to call it j dash. That's at the point -1, 0. And that there is the transformation matrix, which causes anything to be rotated 90 degrees anti-clockwise about the origin. And there we have question number 3, part A and B and C done. And I'll go on to part D in another video. Thank you very much for listening.